Hello and welcome to NetSoft course. My name is Kim Kwai Nguyen and I'm professor at the Department of Electrical Engineering at ATS Montreal. Today I'm delivering the lecture number 8 on network energy efficiency and sustainable management. This is the outline of this lecture. First, I talk about the motivation of the issues of green ICT. And then I review the technology, the issues, and the solutions. Then I talk about some specific framework, for example, adaptive management for device, green abstraction layer for network energy efficiency, green cloud framework for cloud energy efficiency, and then finally I will draw some conclusions. First of all, as you know, the ICT sector is growing very fast, but at the same time is energy war. According to some number that I cite here, only in EU it consumes between 8 to 10% of electricity, and it is responsible for 4% of carbon emissions. As ICT is being used widely in other sectors like, for example, energy, transport, manufacturing, so it is also responsible for the consumption in the other sector if the new technology are not available. Itself, ICT technology is responsible for global emissions. So we consider totally in the equation the ICT itself and its involvement in other sectors. ICT also has been defined as a transformer tool which has abutment potential to reduce energy consumption and carbon emission globally. For example, according to the Smarter 2020 report, if applying all the green ICT technologies, new green ICT technologies, we can reduce up to 60.5% of global GHG emission in 2020. This number is equivalent to 21.6 billion barrels of oil, which is a very huge number, perhaps as large as the reserve of Saudi Arabia. Green ICT technology will create up to 29.5 million jobs because we have to develop new technology. We have new department in green ICT technology in all the companies and global players, for example. In order to apply green ICT technology, of course, telecommunication technology will play the leading role. In order to obtain the optimal result of a process, we have to consider both faces of the same coin. First of all, green ICT, that is, we have to reduce the energy consumption of ICT sector itself. And ICT for green, that is, we have to use new ICT technology in order to green other sectors, in order to reduce third-party waste also. Here that is a chart showing some example. First of all, now we if we apply the more laws that is for every 2 years the processing power of the computer will be double. So we create new equipment. The number of new equipment, number of electronic parts in the world will increase very fast. Now ICT account for 2% of global ICT emissions. State-of-the-art machine threatened by obsolescence. So we have more wasted electronic wastes in terms, for example, computer, in terms of server, and it generates a loss of e-trust. That means, for example, if you are buying a very cheap computer, so we'll replace this very soon. So in that case, you will generate more waste. But if you buy the expensive computer like the Apple computer, then you keep it for a long time, so you generate more trust. ICT has been historically considered as a transformer sector in order to improve productivity in other sector, but also in order to reduce the energy waste and increase the performance. An example, for example, if you are using video conference services, we reduce the transportation services. So as a result, we can reduce carbon emission because, for example, aero transportation consume loss of energy and generate loss of emissions. A newer example, for example, intelligent transport system. Okay, so we can reduce the emission resulting from transport system by, for example, optimizing the route, or you can use a smart electrical grid in order to reduce waste or energy waste generated from the distribution network. For example, if we apply more intelligent algorithm, we will renewable energy close to the generator and close to the consumer, for example. So ICT has been widely used in other sectors in order to reduce energy, but itself, ICT has not applied the same energy to itself. That is a paradox. Okay, so that's why we have this lecture. There are two main motivations that drive the quest for green energy. First of all, the environmental one, as I explained before, because the global warming and other pollution factors, so we have to reduce the consumption of energy from ICT services, and also the waste from ICT services. The second one is the economic one, because when you reduce the number of devices, we reduce the energy consumption, but as indirect result, we reduce also operating costs, for example. If we manage the huge number of links or the huge number of equipment, ICT equipment, so we have to consume, spend more on the OPEX. Okay. So research in green computing technology can be categorized into 6 topics. First of all, storage, consolidation, and server virtualization. That we improve the consolidation of the equipment in order to run, for example, one service on one server. You can run multiple services on a single server, for example. The same mechanism can be applied for storage. The second one is the desktop virtualization and thin client. That is, instead of running the service directly on the desktop workstation, which consume lots of energy, we can run a thin client, like for example Chromebook, and we just display the interface to user while the background process is running on the cloud. Because the network consume less energy than the computing resources, so in that case we can reduce the energy consumption. Printer consolidation will help to reduce the paper consumption in printing services and also energy consumption. Measuring energy usage of ICT equipment, because if we cannot measure correctly exactly the energy consumption, we cannot reduce. How can you break down the consumption, global consumption of the entire service into multiple segments? So it is the challenges. The disposal of ICT equipment is researched on e-waste in general. And finally, energy aware control and management of network, because a network is the substantial component of the big picture. So here we have to reduce the energy consumption using the new control and management technologies. So in the first topic, we talk about the storage, consolidation, and server virtualization. The idea is to decrease the overall number of devices running in the server room. So instead of having multiple servers, we have, let's say, a big server that is hosting multiple services. So as a result, we'll decrease the energy required to run server and storage along with the emissions. We also decrease the cost of future investment, because normally the big server we rest for a longer time than the small server. So we will change the server only after a few years or even 10 years, for example, instead of 2 years. We reduce the time needed for measurement and maintenance that can be translated into the cost also. We simplify also storage space when the data is centralized on only a few systems. So the idea is that we have, let's say, the central storage system, and the server will be bigger, and we run the virtualization platform to host multiple virtual machine instead of running independent small server. The second topic is on desktop visualizations and thin client. The idea is to host the service on the server, virtual server running on cloud, and we access to service via laptop and mobile, because the laptop and mobile consumes much less memory than workstations, and because when you're running multiple services on the cloud, you can apply consolidation or optimization method. So in that case, we can reduce energy consumptions, and we decrease cost of maintenance and management. So some example of thin client, for example, we have a very famous product as, for example, Google Chrome. Now, mobile or in particular smartphone is also so powerful, to run desktop application. So in this case, we can remove many or most of PC workstation in big companies. Printer consideration is all about reducing the paper and ink consumed for printing service by putting all printers in the printing room, and we may, for example, use virtual printer that access to the old printer. Then it will make decision which printer consume less memory or can consolidate the task on a specific printer in order to reduce paper and ink, for example. In terms of measurement, we can manage what we can measure. Okay, so in particular for energy, it's very hard to measure exactly how much energy a virtual service is consuming. For example, if you're running a service on the cloud and we access to this service from the thin client, so the cloud consumes server, but in the same time the network consume energy and client consume energy. So how can you measure exactly the amount of energy consumed by each component? That is a challenge. Energy measurement provides evidence of increasing efficiency in existing and future IT practice. That means, through measurement we can make decision which technology consume better energy. And we have to measure all components, so for example server, network, user device, etc. Even we can go to a lower level, for example at the level of a CPU, at the level of a chipset, at the level of a graphical card, for example, because now many tasks are running on GPU, for example. So how can you break down the total consumption into element consumption? So that is a big problem. In terms of assets and disposal, that is very big issues, but unfortunately we don't have enough time in order to talk about these big issues in this single lecture. So I just have here a chart talking about the waste using in the IT equipment. For example, the increase very fast, and the decreased amount of equipment sent to landfill. Landfills also increase, and normally we have to reduce such e-waste. There are many ways to do it. For example, we can use more powerful server. Perhaps they can be more expensive, but they can last for a long time. So in that case, we can reduce the e-waste. The other ways is that we can reuse or recycle some component or the entire server or ICT equipment. How we can recycle it? So we can apply many mechanisms. For example, we may have a modular design, or we can, for example, consolidate or combine multiple low-profile server in order to run bigger services. The last topic is on the networking infrastructure. Okay, that is the focus of our lecture. Here we focus on bandwidth and provisioning because you're dealing with network. Today, okay, all the operator wants to upgrade the bandwidth availability and also processing speed of network equipment. The networking infrastructure make use of large variety of hardware appliances. They are inflexible, energy inefficient, unsuitable to sustainable reduce time to market of new service. Why? Because simply the telco service is contain a loss of a legacy system, and energy efficiency is not widely used in the current network. So the keyword of our lecture are basically flexibility, programmability, and energy efficiency. When you apply the mechanism, we can allocate resource more efficiently, and at the same time we can reduce energy consumption. The premise are therefore technical and operationally in terms of control and management. The control plane should be quasi-centralized or hierarchical versus distributed, because with a centralized mechanism we can optimize the entire consumption in the network. Okay. If we use distributed control plane, it's very hard to have a energy efficiency mechanism. The management, the control and management plane should be tightly integrated. So when we apply new policy for management, for example, energy efficiency, we can enforce it immediately into device through the control mechanism. So that's why we have to use SDN. Network energy efficiency, okay, when we try to reduce the energy consumption of the network, we have to remember that the quality of service and quality experience should be maintained, because we cannot pay the quality of service of user for energy efficiency. In that case, we have to provide the higher flexibility as well as enhanced control and management capability in order to effectively deal with the performance and power consumption trade-off. Because normally, okay, if we maintain the quality of service and quality of experience, the margin that we can play with in order to reduce energy should be smaller. The traditional control and management mechanism did not allow us to do it, because, for example, distributed control plane require time for conversions, so we cannot play with it in order to reduce energy consumption. If we are using SDN, because this is a centralized control mechanism, so we can apply the optimization mechanism more efficiently. A new dimension of energy earnestness should be added to the network design operation. That is, for example, a new module of green energy, green control would be designed to add to the control plane or management plane of the network. Why there is a problem of energy inefficiencies? First of all, because the current internet infrastructure and technology and protocol are designed to be extremely over-dimensioned and available 24%. That is, you can imagine the link or the equipment when they are activated, that they will be functional at 100% of the power. Traditionally, there's no mechanism in order to increase the performance according to energy consumption. So basically, when you turn on a device, it will be at 100% of power immediately. And more importantly, links and devices are provisioned for rush hour load only. All the operators are most concerned about the peak load. So, for example, in the holidays time, okay, there are more calls, so the infrastructure should be provisioned or over provisioned in order to deal with the peak hours. And the overall, as a consequence, the overall power consumption in today's network remains constant. Okay, so it's not changing. So here you have an example. Normally, you can see in all devices, here the power consumption is almost constant, while the actual traffic is fluctuating a lot. So that is the issues of today's network. So in reality, okay, the percentage with regard to the peak level, we are not always consuming energy at the peak level. The profile of traffic running on the network in both North America and Europe in this chart show exhibit regular. For example, in the morning, okay, the traffic increase very fast, and during the night, okay, it's lower. Within the data center, we can observe the same phenomena. For example, the traffic is very time dependent. Here you see the peak during the daytime, and during the night is a lower traffic. And in the data center, there's a loss of underutilized link. You know, for example, in the aggregation level, there are lots of links that are not used because in the data center we can deploy a loss of link without paying loss of cost. So normally, okay, the network within the data center is always over provisioning. And in data center, okay, all links are very reliable. They are filling with losses. So there's a loss of redundant there. Okay, and if you apply the better management mechanism, we can reduce the consumption in terms of link. So how to manage this trend? Today, network infrastructure is characterized by the design to capable to deal with a strong request and constraint. So the most concern of the operators are performance. For example, large load, very low delay, high availability. While the service characterized by high variability of loads and resource requests. For example, bottlenecks, rush hours, etc. The feasible solution that we can think about in order to reduce consumption. First of all, we talk about the smart power management. So instead of having a energy consumption that is fixed, we may changing the energy or the power of the device according to the fluctuation of the service request. So what we have to deal with is very fast, because you know, okay, traffic is running very fast in the network, and we have to apply immediately the policy or control mechanism or optimization problem. So it's challenging. The second solution is flexibility in resource usage. That is a new method in which you apply virtualization to obtain an aggressive sharing of physical resources. That means, okay, we have to share resources more efficiently among all the users. If some users are not using resources, the resources should be taken back and distributed to other users. So a breakdown of energy consumption in network. If you look into this chart, we can see the access node, transport node, and core node. Okay, the core node are fewer in terms of numbers, but they consume a lot of energy. For example, 30% of energy consumption only for here. Okay, fewer nodes. the access network consume the majority of energy, 70% of total energy of the network in general. However, they are very large in the number. You can imagine in the access network, there are lots of base station, there are lots of ICT, IoT equipments in general. When we apply energy efficiency, we have to take into account the fact that each individual equipment in the access network consume smaller energy, but the total number is larger. While in the transport and the core network, each node consume lots of energy, but however they are small in terms of numbers. The focus will be on transport and core network because it's very hard to reduce the energy consumption on each small device of the access layer. So within the data center, we can see the IT equipment consume about 40% of energy. The power delivery, like say the PDU, the power unit, etc. They consume 30% of energy, and the cooling equipment consume about 30%. If we are using the air cooling, it consumes more than, for example, water chilling. Now focus on the this part, 40% of IT equipment. This number is broken down into 60% of computers, 20% of storage, and 20% of communication. That means the network equipment. So the computer servers consume the majority of the total amount of energy. This number, 60%, will then be broken down into 35% of CPU, 15% of CPU, memory 15%, hard disk, accessory 50%, and 20% of PCU loss. We can see, first of all, ICT equipment consume the majority, and then in this number, the computer consume the majority, and then the server, the CPU. Those are number that we have to remember, because if you want to reduce energy consumption, first of all, we have to focus on CPU, and then we focus on the computer, and then we focus on the IT equipment in order to have the highest performance. The energy aware approaches. The idea is that each equipment or each data center or network device may have multiple profile. The standby profile, that is the state in which the device consumes near to zero power. You can call it idle or long. For long period, you can call it, for example, hibernate in the PC workstation, for example. And then we have idle state, we consume low power energy, and then we have active state. Depending on the load, we can have the state that consume less energy and the state that consume higher energy. That is the design of network data center equipment. What you have to do, you have to do re-engineering in terms of energy efficient physical element. Then we will create the device that's supporting multiple energy profile, and you have to reduce the complexity in all the devices and in the entire network in general. The mechanism that we are applying is dynamic adaptation. That is, we adapt the quality surface of the performance of the device according to the power consumption. In general, the maximum power saving is obtained when the equipment is 100% off, that is turn off. But in this state, that is the standby state. The performance is actually zero, and the equipment can do no task. So we are not focusing on this one, of course, because we have to maintain the network at least in the active state. The best performance equipment may provide is under no power limit mode. So that is in the active state 1, for example, here. So we have the best performance, but however the consumption is highest. So the energy efficiency, where can apply it? We apply it in between, okay, between the 0 and between the highest one. We are playing within this margin. The dynamic adaptation, we are using two approaches in the device. First of all, is a dynamic power scaling. So we apply for some traffic handling, queuing, shipping, policing, in order, let's say, to reduce the power. In same time, okay, we reduce the traffic going through the links. A smart standby. Here we put the device in the standby mode, but it will be woken up immediately when there is the new task. The dynamic adaptation, so the device can be applied using, for example, link protocol and traffic shipping. At the device level, you can physical, economic, logical function, and the technology that we can apply a dynamic adaptation can be at the core level, at the metro, at the access level, and at the edge level. Here in this chart, showing the margin where we can apply the dynamic adaptation in the chart of quality of service, because the idea is that we have to maintain the quality of services. In the standard operation, here you have some task, and this is power consumption. The power consumption is constant because the server is at the active state number 1, so the power consumption is constant. If we're applying, for example, idle logic, for example, if there's no task or no traffic, we will turn off temporarily the device. So we have, let's say, when the task, immediately, okay, the device will be active at the highest level. Okay, and then if there's no load, okay, we need some time in order to slow down the performance of device, and then the device will rest in the idle state for a while. So in that case, you can save some energy. The power scaling is the mechanism in which we reduce the quality service. That means, for example, in this case, we may reduce the workload, we will reduce the bandwidth, and in the same time, reduce power consumption. That means we maintain the device at a power state which is not the highest one, not red one. It consumes energy at yellow level, that is a medium level, but in the same time it takes more time, to process the data. So in that case, we can also save energy, because totally here, because if we count the total amount of energy here, okay, it will be smaller than in the first case. The third one, we combine both idle logic and power scaling. That is, we maintain the device at the medium level of power consumption, and if there is no workload, so we turn it off temporarily. So if we apply both in the same time, and we have optimization mechanism here, we save the most energy possible.